I'd like to talk about how we determine the form of the rate law. And in this video, we're talking about the differential rate law, the one that shows how the rate of reaction depends upon concentration. So let's consider the decomposition of dinitrogen pentoxide and water to form aqueous nitrogen dioxide and oxygen gas. We can write a hypothetical rate law that defines the rate as the decrease in concentration of N2O5 with respect to time, and we can simply say we know that's going to be equal to the rate constant times the concentration of N2O5 raised to the power of N, which is the order of the reaction with respect to N2O5. So in order to determine the full rate law, we need the numerical value of K, the rate constant, and we need the numerical value of N, the order with respect to N2O5. So can we deduce N from the overall stoichiometry of the reaction? For example, because in this reaction, the coefficient before N2O5 is 2, can we deduce that it must be second order with respect to N2O5? Well, life sure would be easy if that were the case, but it ain't. No, you have to do experiments. So the experiments we'll do will involve measuring and graphing the concentration of N2O5 as a function of time. So if we carry out the experiment and watch the concentration of N2O5 decrease with respect to time, we see that after, about 200 seconds, when the concentration is dropped to 0.90, the instantaneous rate of reaction is 5.4 times 10 to the negative fourth mole per liter per second. But when the concentration is dropped to 0.45 moles per liter, the rate is decreased to 2.7 times 10 to the negative fourth. And the question is, can we determine anything from that? So look very carefully. The concentration has decreased by a factor of 2, and the rate has also decreased by a factor of 2. So how does the rate depend upon concentration? So as the concentration decreases, the rate decreases. And in fact, we can see the fact that the rate decreased by the same factor as the concentration, it must be the case that the rate is directly proportional to the concentration. That allows us to deduce the fact that N, in this case, is equal to 1. Simply by seeing that the rate is directly proportional to the concentration allows us to deduce that this reaction is first order with respect to N2O5. So I can write the rate law as decreasing concentration of N2O5 with respect to time is equal to a rate constant times the concentration of N2O5. So how do I determine the value of the rate constant? Well, I know values of rates and I know values of concentrations, so I can simply rearrange. I can simply say that K is going to be the rate of the reaction using either of those 2 points divided by N2O5. I'll simply arbitrarily choose one of them. So 5.4 times 10 to the negative fourth moles per liter per second, divided by the concentration at which the reaction had that rate, 0.90 moles per liter, and I get a value of K equal to 6.0 times 10 to the negative fourth. Moles cancel, let's get some color in there. Moles cancel moles, liters cancel liters. The unit I'm left with is reciprocal seconds, which we said is the unit for a first order rate constant. Okay? Now, this obviously was a made-up case, and nothing in life is going to be that simple. So we are going to use a much more general method for determining the order with respect to each reactant in the case where there's more than one reactant, and it's called the method of initial rates. Very simple, very powerful. It is a method for determining the order of the reaction with respect to each reactant, and we do so by carrying out a series of experiments, and in each experiment we measure the initial rate of reaction, that is the average rate over a short interval early in the reaction, using varying initial concentrations of different reactants. And how the initial rate depends upon the initial concentrations allows one to deduce the order individually with respect to each reactant. Okay, so let's take an example. Ammonium ion reacts with nitrite ion to form nitrogen gas and liquid water. We'll begin by writing out a hypothetical rate law in which we simply write lowercase k for the rate constant and N and M as stand-ins for the orders with respect to ammonium and nitrite. And notice that we define the rate of reaction in terms of the decrease in concentration of ammonium. So we're going to measure the rate of reaction using varying initial concentrations of ammonium and nitrate. And I've got my data on the next slide. So once again, there's my reaction at the top. There is my hypothetical rate law. Remember, we're trying to find three things: K, N, and M. And here are our data. Okay. In experiment number 1, I choose these initial concentrations of ammonium and nitrite, and I measure the initial rate. Again, the initial rate is the average rate of reaction over a short interval early in the reaction. In experiment number 2, I hold the initial concentration of ammonium constant. So I take it out. It's a control. I increase the initial concentration of NO2, and I see the initial rate increases as well. In a third experiment, I hold the initial concentration of nitrite constant, and I increase the initial concentration of ammonium, and I see the initial rate of reaction increases as well. We don't need to do any calculations. We can simply tell, by eyeballing it, the orders with respect to ammonium and nitrite. So, when the initial concentration of NH4+ is constant, and the concentration of NO2- doubled, what happened to the initial rate? The initial rate also doubled. That allows us to deduce that the order with respect to nitrite, M, is equal to 1. If increasing the initial concentration of one reactant by a certain factor while the other is held constant causes the initial rate to increase by the same factor, the rate is directly proportional to the concentration, and therefore the order is 1. Now, comparing experiments 2 and 3, when the concentration of nitrite is held constant, and the concentration of ammonium is doubled, I see the same thing. The initial rate doubled, and therefore I can conclude that N is equal to 1. So we see from the experimental data that this reaction is first order with respect to both ammonium and nitrate. Okay? Now, the question is, how do we calculate K? Quite simply, we simply say K is equal to the initial rate divided by the product of the ammonium concentration and the nitrite concentration. And I can take any one of those data points. Let's take the first one, 1.35 times 10 to the negative 7th moles per liter per second, divided by the product of the concentrations of ammonium and nitrate, 0.100 mole per liter, times 0.00500 mole per liter. Wouldn't you know, I didn't do this calculation before starting the video, and there's no pause button, so let me get my calculator. You can do it along with me to make sure I don't make any mistakes. And I get a value of 2.70 times 10 to the negative 4th. Let's see my unit then. Moles cancel moles, liters cancel liters, and I'm left with a unit of liters per mole per second, which is what we said would be the correct unit for a second order rate constant. Now you may ask yourself, how is this a second order rate constant? Well, we would say that this reaction is first order with respect to ammonium, first order with respect to nitrate, second order overall. Okay? Now, in this case, we were able to simply look at the data and see very simply that doubling the initial concentration of one reactant while holding the other constant caused the initial rate to double, blah, blah, blah. What if it's not that simple? Well, let me show you the mathematical way of doing this. It's a bit more detailed, but it will always work. So the reaction chlorine dioxide reacts with hydroxide to form the chlorate anion plus the chloride anion plus water. And we have the same setup here. We've got 3 experiments. We vary the initial concentrations, hold the other one constant, and measure the initial rate. So here's how we're going to do it. I'm going to write a hypothetical rate law. So I'm going to say the decrease in concentration of ClO2 with respect to time is equal to some rate constant times the concentration of ClO2 to the A power times the concentration of hydroxide to the B power. Again, our goal is to find numerical values of K, A, and B. I'm going to write out the rate law for experiment number 2. That's going to be K times the initial concentration of chlorine dioxide in experiment number 2, 0.100. In the interest of space, I'm going to leave out units, but you know that you can't do that, right? Sorry. To the A power times the initial concentration of hydroxide, 0.100, to the B power, which is equal to 0.230 moles per liter per second. I'm going to write out the hypothetical rate law a second time, now for experiment, sorry, not experiment number 3, but experiment number 1. And that's equal to K times the initial concentration of ClO2 in experiment number 1 to the A power times the initial concentration of hydroxide in experiment number 1 to the B power, and that's equal to 0.0575. Now, do you know what I'm going to do with these two equations? Yes, you can see it. I'm going to divide them by each other. And now, because the initial concentration of hydroxide is being held constant, I can simply cancel all of that, the concentrations and the order B. Now I can simplify this by simply saying, oops, switch back to my preferred color. I can simplify this by saying rate 2 over rate 1 is equal to, oh, what else can I cancel? Of course, I can cancel K. Is equal to 0.100 over 0.0500 to the A power. Well, I can evaluate the ratio of the rates. That's simply equal to 4. What's inside the parentheses? 2 to the A power is equal to 4. A is equal to 2. So that allows us to deduce that the reaction is second order with respect to ClO2. Now, I still need to figure out the order with respect to hydroxide, so I'm going to do the same thing now with experiments number 2 and 3. So, rate 2 over rate 3 is equal to K times 0.100 to the A power times 0.100 to the B power divided by K 0.100 to the A power times 0.0500 to the B power is equal to 0.230 over 0.115. Now, because the initial concentration of ClO2 is being held constant, I can cancel it, but even if it weren't, it doesn't matter because we know what A is. Okay, we could have simply plugged in 2 for A, be a little bit more math, but, you know, wouldn't be that bad. So now I'll cancel it anyway. I'll cancel K, I'll cancel K. And that gives me now rate 2 over rate 3 is equal to 0.100 over 0.0500 to the B power is equal to 2. What's inside the parentheses is 2. 2 to the B is equal to 2. So that lets me deduce that B, the order with respect to hydroxide, is 1. Okay, so I've got my orders, and now the last thing to do is to solve for the numerical value of the constant, of the rate constant. So simply to write out the equation, the rate law, the decrease in concentration of chlorine dioxide with respect to time is equal to K times the concentration of chlorine dioxide squared times the concentration of hydroxide. Now to solve for the numerical value of K, I'll simply rearrange. K is equal to the rate over ClO2 squared times the concentration of hydroxide. I'll just randomly choose one of them, 0.0575 mole per liter per second, divided by 0.0500 mole per liter squared times 0.100 mole per liter. I can see that one of the moles per liter is going to cancel, but I'm still going to have moles squared per liter squared in the denominator. So when I calculate my value, I get K equals 230 liters squared per mole squared per second, which we said in the previous video is the unit on a third order rate constant. Okay, well, how is this a third order reaction? Well, simply look back up here at our rate law. We would say that this reaction is second order with respect to chlorine dioxide, first order with respect to hydroxide, third order overall. Now, once you have the rate law and the numerical value of the rate constant, you can use it to calculate the instantaneous rate of reaction given any concentrations. Remember, the whole point of a rate law is it expresses the rate of reaction as a function of concentration. So I can actually calculate the expected initial rate when I'm given these concentrations. So I'll write out my rate law again. Oops. The decrease in concentration of chlorine dioxide with respect to time is equal to K times the concentration of chlorine dioxide squared, to the second power, times the concentration of hydroxide, where K has a value of 230 liters squared, moles squared per second. So anytime there's a problem where it says give the full rate law, it's fine to write it like this. Write out the rate law with K and then separately indicate the numerical value in unit of K. Well, now I can simply take the rate law and plug in what I've got. 230 liters squared, moles squared per second for K, 0.175 moles per liter for the concentration of ClO2, and 0.0844 moles per liter for the concentration of hydroxide, and that gives me an instantaneous rate of reaction of 0.594 moles per liter per second. Okay? So that's it for the method of initial rates for determining the rate law for a reaction that has multiple reactants. And in the next video, we will learn about integrated rate laws. See you then.